Hello everybody, welcome to our video for the one and only problem from quiz 8. So we had only one problem because this one problem is lengthy enough in its solution. The statement is pretty short. We want to find a power series solution to a second order differential equation, non-constant coefficients, so y double prime minus 2x y prime is 0. So the way we proceed is more or less the same in all these situations. We're going to assume that we do have some sort of power series solution. So we assume that y is equal to some power series coefficient we'll call a sub n. Right. In this particular case, we're very justified in using this method because of something which is sometimes called Fuchs' theorem, which says if you have a second order differential equation and the leading term is 1 and the coefficient, quote unquote, in front of the y prime is some function of x, which is analytic, or if you like, has a power series at around whatever the center of your power series is going to be, in this case 0. And then we even could have a y term, and that also should have a coefficient, which is an analytic function at the center of your power series. In this case, it's plus 0y, so the 0 function is not a problem. It has a power series, namely the 0 power series. But if you're in that case, then you know that this method of assuming y has a power series, you can get a solution to the differential equation by inserting this power series into the differential equation. We also know we should get sort of two components at the end that will have a generic coefficient, which will come from the A0 and the A1 terms. We can even say more about the radius of convergence. So Fuchs' theorem not only is going to tell us we're going to get a solution, all right, so we will get a solution, but also in this case, because our coefficient functions, which are negative 2x and 0, which you don't see, of course, they have power series expansions, sort of trivially, and so the radius of convergence for both of those power series is infinity, which means that the power series solution to this differential equation is actually going to be infinite. Now, the question didn't ask us to get the radius of convergence here, but I just think it's a nice thing to point out as long as we're using Fuchs' theorem. All right, so what we want to do, though, is take this power series for y and insert it into our differential equation. So I have a y double prime, and I will just insert for y this power series. Oops. And there we go, nth power. And we'll take a double derivative. Minus 2x times, all right, now we're going to take a derivative of y. Okay, and I'll copy the power series expansion for y in. All right, and so now we just do the algebra here. So if I take two derivatives, then I'm going to get, well, let me leave this blank for a moment. It should be 0, but we're going to mix it up a little bit. So two derivatives, I bring down an n first, then an n minus 1. A sub n, x to the n minus 2. This will go to infinity. And let me handle the other one. So let's see. Again, we have a sum. It should start at 0, but let's leave it blank for a moment. The n comes down, and I'll get n a sub n x to the n minus 1. But this 2x comes in. So first, there's a 2, and the x will turn this x to the n minus 1 back into an x to the n. And this will go to infinity. All right. Now, in order to put these together, I would like to ensure that these exponents are the same. That'll make it a lot easier to put these things together. So what I'm going to want to do in this first one, I want to turn this back into an x to the n, which means I need to replace all my n's with n plus 2's. All right. Now, if I do that, then at the end of the day, what's going to happen with this index? Well, when I increase my n's by 2 here, I'm going to have to decrease my n in the summation. If I decrease it from 0, it'll go down to -2, and that doesn't feel so good. Let's take a look though at what actually happens here. So if I wrote n equals 0, the very first sum end would have a 0 for n, which means the sum end would just be 0. So I don't really need to put that in. What if I made it a 1? If I made it a 1, then the second factor would be 0. And so the second sum end would be 0. So I don't really need that. I can actually start at 2. All right. And that makes me feel better because when I increase these n's by 2, right, everywhere here, I have to decrease this by 2. It goes back down to 0. All right, that feels better, right? So I still haven't put in this number, but we'll handle that in a moment. So when I re-index, I'll go from 0 to infinity, n plus 2, n plus 1, an plus 2, x to the n. So notice I'm replacing all of my n's everywhere in this first series with n plus 2. All right, and you may not say, well, wait, why if I increase the n's by 2 do I have to decrease over here? Well, that's sort of a little mnemonic that I taught in class, but we can see it just by plugging numbers in. So for example, here when n is equal to 2, then this exponent becomes x to the 2 minus 2, which is x to the 0. So the very first summand needs to have an x to the 0. Well, down here I have x to the n, so my first n needs to be 0. So I can check it that way. All right, now what about in this second series? Well, I want to start at 0. And, well, it was supposed to be a 0 already, so hey, I'll just leave it as 0, right? That makes me feel good. Note that the very first summand will be 0, right? n equals 0, we'll come in here, make this n a 0, and you won't get anything, but it doesn't hurt to have that extra, and it lets us line up these two series now, right, in the indices. So I can copy that down. Again, now I check, I have the same exponents. I check what my starting points. They're both n equals 0. So I can combine these without any further fuss. Okay, so we do that, and I'll get a sum from 0 to infinity. All right, both of these have an x to the n, so I'll wait to write that till the end, and I get n plus 2, n plus 1, an plus 2, minus 2n a sub n, and then all that is multiplied by x to the n. Okay, so I have a series, right? This is a power series, which is equal to 0. And we should recall, we've shown that when we have a power series, which is equal to 0, this implies, right, that the an is equal to 0 for all relevant n. Okay, so this implies now that our coefficients, right, everything in front of the x to the n, are all 0. So n plus 2, n plus 1, an plus 2 minus 2n an is equal to 0. And this is for all n at least 0. Okay, so our general method from here is to solve for the coefficient with the larger index. So in this case, that's n plus 2. So I have an plus 2 equals 2n over n plus 2 times n plus 1 times an. Of course, normally you would think to leave the an up top. It turns out for what we're going to do next, it's a little nicer to write the an on the side. Okay, and again, this is for all n at least 0. Okay, now we notice that there is a jump in the index from n to n plus 2. That tells us if we know something like a0, we'll be able to use this recurrence relation to get a2, and then a4, and a6, etc. But that'll miss all the odds, right? So we're going to need another starting point, like a1, and a1 then will give us a3, and a5, and a7. All right, so let's try this. So we want to start from a0 and a1. Those are what they are. We're not going to be able to write those in terms of other things. And according to Fuchs' theorem, we shouldn't expect to, right? In Fuchs' theorem, we always start with an a0 and an a1 as multipliers. Okay, so what about a2? Well, I use this recurrence relation. All right, so you start with n plus 2, that's my 2. So I get a 2 times, now n is 2 less than n plus 2, right? So 2 less than 2 is 0. Okay, over, well, n plus 2 is the same number, n plus 1 is 1 less, and then I get a sub 0. All right, but that 0 is there, right? So this whole thing is actually just 0. Ah, this makes us feel really good, because if I try to do the next one, right, a4, I know it's just going to be some multiple of a2, right? Something, it doesn't even matter what it is, times a2, but a2 is 0. All right, and so proceeding in this way, every even coefficient is going to be 0, all right, provided n is at least 1. All right, of course, the a0 may not be 0. Okay, that's a key point here, right? The zeros only start at a2. Okay, cool. How about a1? Well, it is. It's a1. So we go to the next coefficient, a3. We know that will be 2 times, all right, again, this n is 2 less, so a1, or not a1, but 1, over, okay, we write the same number, which is 3, 1 less, that's 2, times a1, right, because the n is 2 less than n plus 2. Okay, let's try a5. So a5 will be 2 times, now let's see, n is 2 less, so 2 less than 5 is 3. Then the same number, so that's 5, 1 less, that's 4, and then we write an a3. But we already know a3, so we can write 2 times 3 over 5 times 4, times, okay, my a3 was 2 times 1 over 3 times 2 times a1. All right, and we've written a5 in terms of a1. All right, I think I'm starting to spot a pattern, but let's write one more term down just to make sure. So let's see here. So a7 will be 2 times, all right, 2 less than 7 is 5. Copy the 7, 1 less than the 7, 2 less than the 7, right, a sub 5. Okay, but now I copy the first bit, and a sub 5 I just computed. It was 2 times 3 over 5 times 4, and 2 times 1 over 3 times 2, and an a1. And yeah, okay, I see the pattern now. All right, in the numerator, you get a bunch of 2's, right, 1 for each term, and then you're counting up by 2's starting from 1, so 1 times 3 times 5. And on the bottom, well, actually, you're just getting everything, 2, 3, 4, 5, 6, 7, right? You're getting a factorial. Okay, so my prediction then for the generic odd term, which we can write as the 2n plus first term, is going to be, well, okay, we would have a bunch of these. Well, what's going to happen on the bottom? We should just get a factorial, right? So there's a 7. Hey, that's the highest number. So we'll get 2n plus 1. That's this number, factorial. How about on top? Well, let's see. I get a 2 every single time, right? Now, how many times are there? Well, if I write the number like 7, I could think of this as 2 times 3 plus 1. There's that 3, that's my n, and that's how many 2's I have. So I should get n copies of 2. All right. Then the other piece I get is, well, you got to start from, let's see, 5 was 2 less than this number, so we'll start from 2n minus 1, and we multiply down to 1, but we skip, okay? So there is a common notation for this. I call it double factorial. So when you write something, right, 2n minus 1 double factorial, this means you start at 2n minus 1, and then you drop down by 2 each time. So then 2n minus 5, and you keep going until you get down to 3 and then 1. Okay, and then we have an a1 over here. Okay, I'd like to do one more simplification here. No, let me add in here for all n, at least 1. I'd like to do one more simplification. So I notice here I'm going to multiply all the numbers from 1 up to 2n plus 1. And here I'm multiplying just the odd numbers from 1 up to 2n minus 1. So there's going to be some cancellation here, right? Let's write this to the side. So there's my 2n minus 1 double factorial. Let's write this over 2n plus 1 factorial. So over here, I would have 2n plus 1. And I'm going to write this in just a funny order. I'm going to do all the odds first. Dot, 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 3, 1. And then I'll write the missing evens. Okay, so then I have 2n and 2n minus 2 and so forth down to 4 times 2. And so what I notice is I actually get a whole bunch of cancellation, right? All these odd terms except for this 2n plus 1. And then the evens, those also stick around. Okay, so if I do that cancellation, then let's see what's going to be left over. Well, okay, let's not forget the 2 to the n here. Okay, let's put a 2 to the n in. If I do this cancellation, then on top, all I'm left with is a 2 to the n. And on the bottom, I have 2n plus 1. And then all of these evens, 2n, 2n minus 2, and so forth, down to 4 times 2. Okay, but I could divide all of these evens by a 2 and cancel, right, with a 2 from the top. And so when I do that, all these 2's go away, and I'll end up with, okay, there's this 2n plus 1, but what's left over? Well, I have n. Now this 2n minus 2, maybe we think about it as 2 times n minus 1. When I cancel a 2, I get n minus 1. And this will keep going down all the way to 3, 2, 1. So actually this piece is just n factorial. So actually I can simplify this as 1 over 2n plus 1 times n factorial, and then still times a1 for all n at least. We said 1 here, right? But this is actually true for 0. Okay. Actually, well, it's a little bit funky when we do the 0 case here because we'd end up with -1 double factorial, which for the purposes of this argument, I guess we would probably want to not handle. However, in the special case now where n is 0, we get 1 over 1 times 1 factorial times a1, which, well, that is the n equals 0 case, right? We get a1. So this now works actually for n greater than or equal to 0. Okay, now that's our suspicion based on the pattern. A proof, right, is just going to come through induction. So we can prove this by induction. Okay, so let's do that proof actually. So assume, we already have base cases up the wazoo, so let's assume that it was true for a 2n plus 1. Let's go to the next term. That would be a 2n plus 3. So we know that a 2n plus 3, well, let's see, we better get our recurrence relation. All right, let's copy that so we can see it. So bring that down. Oops, down here, and put that in. All right, so we can see our recurrence relation. So let's see, this is supposed to be 2 times, all right, the number which is 2 less than 2n plus 3. So that'll be 2n plus 1 over, we copy the number, 2n plus 3. 1 less, that'll be 2n plus 2. And then our a sub n, which is, that's the one that's 2 less. Well, we already know that's 1 over 2n plus 1 times n factorial times a1. All right, well, already I see a 2n plus 1 and a 2n plus 1 are going to cancel. And so what's left over? So I have 2 over 2n plus 3 times, now let me write this 2n plus 2 as 2 times n plus 1. That seems nice. And then I still have this n factorial. Okay, so this 2 and this 2 can cancel. And so then I have 2n, this 2 canceled, so it's a 1. And I have 2n plus 3, but now n plus 1 times n factorial is n plus 1 factorial. And then we still have the a1. All right, so that's actually what we wanted to prove, right? You get to copy this number to the bottom. And then our n in this case, right, we could view this as 2n plus 1 plus 1. Our new n is n plus 1, and that's the factorial we get on the bottom. All right, so we prove this by induction. Fantastic. So now we get our solution. So therefore, our y can be written as, well, okay, so first you have this a naught. All right, and we didn't have to worry about any of the other even coefficient terms, but the a naught, that still lives. All right, then we're going to have a power series, and the coefficients, right, they all looked like, well, this, except in the place up above. Let's go there. There we go. They all looked like this. Notice they all have an a1 in them, so let's factor the a1 out. So now I have a series. I'll go from 0 to infinity, and my coefficient is 1 over 2n plus 1 n factorial. And I'm looking right at the odd exponent x's here, so x to the 2n plus 1. All right, and that is my power series solution to the given differential equation. One could check this by taking derivatives, right? Just plugging this into the differential equation and making sure you get 0, and you can check and it'll work. All right, very good. Have a wonderful day.